Good morning, students. Welcome to Wednesday, May 13th, 2020. Today, we're going to talk about sedimentary rocks. So you should be able to explain how sedimentary rocks form. There's some vocabulary associated with that. And then, in talking about sedimentary rocks, this is much more involved than what we did yesterday, talking about our igneous rocks. We're going to talk about how sediments form. And so there's processes of weathering, erosion, and deposition. And I would want you to be able to define those words, weathering, erosion, deposition, and be able to give examples of those that I'm going to go through. So, a reminder that sedimentary rocks are rocks formed from small pieces of pre-existing rock. I'll come back to that. So those pieces of pre-existing rock are what we call sediments. So sediments are fragments. Actually, there's different types of sediments. Fragments of other rocks. Okay, so if we have a rock that's been broken down into pebbles or sand or clay, and the only difference between those terms is the size of the particles. Okay, clay is referring to the smallest of particles. Silt would be a term I didn't put on here, but it's in between. It's a little bit bigger than clay, but smaller than sand. Then we get to sand, and then pebbles, and then you get boulders, etc. These are just terms that geologists use for the size of the rock particles. Now, sometimes you can have organic material. So we said that minerals come from non-living things. But there are organic materials that sometimes do get incorporated into rocks. Okay, so rock, the word rock didn't necessarily say not from living things, the word mineral did. Chemical precipitates. What this means is that you had stuff that was dissolved in water and then it somehow came out of the water. The water evaporates away and you have these solids that are left behind. I'm going to throw a couple of words out here. If you have sediments coming from organic material, that means it was once living material. Those sediments are called bioclastic. And so sediments that don't come from living things, those are called clastic. And so you may see that in your reading assignments and things like that, where it refers to clastic or bioclastic materials. Bio means living. Organic means living. They're two terms for the same thing. We had a brief rundown of these different types of rocks the other day, and you know, sedimentary rocks formed by the compaction and cementation of the particles, so they're squeezed and glued together. So I had this this rock that I made. Okay, it's very rock-like. I think it's a really good example. It wasn't my original intent, but this was sand and some iron filings and some sugar that I mixed together, and I added a little bit of water. And then I packed it down, so I guess I did a little bit of compaction, a little bit of squeezing, but I didn't have to really let this go because the sugar originally dissolved in the water, but then as the water evaporated away, the sugar came back out. It precipitated back out of the water, and it stuck to all the other particles and effectively glued all the particles together. And now we have a very rigid rock-like substance. So that's the process that happens a lot of times in sedimentary rocks. You have pieces that get piled up, buried, squeezed under pressure, and then maybe some gluing back together. Now you could also have situations where minerals just precipitate right out from solution and without gluing a lot of other stuff. These can be very pretty things. But I think quite often this process of materials precipitating out is what makes the glue that holds other sedimentary rocks together. So a couple of pictures here. Hopefully it shows up on the screen okay. So here's a rock formation. I mean, these are trees in the background to give you an idea how big this is. But you can see these layers. And so what happened is you had this big area where bits of rock were deposited over thousands, very possibly millions of years. And the pressure is squeezing it all together, and maybe there's some of that cementation action where maybe some liquids containing materials move through it. The liquid evaporates, and the stuff is glued together and turned into solid rock. Now, solid rock doesn't mean you can't break it. We can break rocks. So here's a little piece of rock from sedimentary rock, and within this piece you can still see that the bandings, and I think you can see in the picture that there's some coarse grain. If you took your fingernail and even rubbed over that, you might be able to rub bits of it off, just like with my homemade rock here you could do. Here's a picture of another sedimentary rock where you can see the all sorts of different size. This one has all fairly small grains. This, I'm guessing, would be considered sandstone. This is called a conglomerate. This has got all different size particles, lots of pebbles in it, along with smaller bits, and they've all been kind of compacted and glued together into a solid mass. There's a rock. Oh, then we get into the chemical precipitates. These are the really pretty ones. These are called geodes. And you can see on the outside, if you just saw the outside of this rock and you didn't know what you're looking for, I admit I wouldn't know what I'm looking for. You just have a rock, right? But you crack this open and you find this beautiful inside, these crystals. That one has, purple crystals, clear crystals, purple crystals, clear crystals, blue crystals. Why different colors? Different minerals. Okay. What happens here is these are actually associated with volcanoes. Volcanoes put out a lot of gases. So imagine as magma is cooling and there's gas bubbles. And so you literally get an empty space within the rock because of a gas bubble. Now give it thousands of years and water works its way down through the rocks, and water seeps in and fills this bubble. And that water gradually disappears, it evaporates again or something, and it leaves behind minerals that were dissolved in the water. And over huge lengths of geologic time, we build these beautiful crystal structures inside these rocks. They really are gorgeous. This purple stuff is, I believe, called amethyst. It's a semi-precious gemstone. I don't know what the blue is called, other than it's really pretty. So, in order to have sedimentary rocks, we have to have sediments. How do sediments form? Okay? We're going to talk about the process of weathering, erosion, and deposition. Wrong way. So, weathering, okay? Definition, flat out. Weathering is the breaking down of rock into smaller pieces. Now, you often hear the terms weathering and erosion together, and sometimes they get literally mixed together where people say erosion when really the right word is weathering. Okay, so the breaking down, if I have a big piece of rock and a chip breaks off of it, that's weathering. It's breaking down. Erosion we're going to get to, but erosion is where those pieces then get moved around. Okay, so weathering is breaking down. Now we can talk about physical weathering, also called mechanical weathering. There's physical forces. It wouldn't be an example of natural weathering, but if I took a hammer out to a great big boulder and just started pounding on that boulder, breaking off chips, that's physical forces at work. That would be physical weathering or mechanical weathering. Chemical weathering would be where stuff becomes dissolved in water or things like that. So if I had a rock and I have, maybe I'm making a water feature in my garden and I have a trail of water that I have flowing over the rock. Now let that work for a couple 100,000 years, and I may actually have a groove in my rock where that water has continually wore away at the rock. That takes a little bit of time. Now, some rocks are more soluble than others. Some rocks are just plain not soluble. It's a matter of what material you have. Certain substances are soluble. Maybe imagine this. Maybe you've seen a mineral block that you might put out for cattle or for deer. And if I had that block and I let a trail of water go across it, over time that would wear a trail in it because that material is somewhat soluble in water. So we're going to look at some examples here of physical weathering. And the first one is going to be called ice wedging, or also called frost wedging. And this is an example that's true to Wisconsin. It's, among other reasons, it's probably one of the reasons why we're always going to have problems with our roads in Wisconsin. So let's imagine we got a little crack. I don't know what made the crack, but let's imagine we have a crack. And some water seeps into that crack. And it's maybe warm enough in the daytime that water seeps in, but at night it gets below freezing. This time of year, we just had several days that did this. So at night, that water freezes. And you may remember from other things that water is one of the rare substances that expands when it freezes. And when that ice expands, have you ever had a can of soda, maybe sitting out in a garage in winter and it's unheated garage and the soda can blows up? It's because when the water expands, it has a tremendous amount of pressure and it can blow that can up. Well, that water is expanding and it's pushing on the rock. And what can happen is it makes the crack a little bigger. Now, the next day, sun comes out, that ice melts, more water seeps into the crack, cold comes at night, freezes, expands, pushes on the crack. Next day, ice melts, night comes, water freezes, pushes on the crack. Now just repeat that a few 100,000 times. And the crack gets bigger and bigger and bigger until the rock might break. Another example of physical weathering, root wedging. So let's again start with a little crack. Something made a crack in a rock, and a little bit of dirt or soil got in there, and a seed dropped in it. And the seed starts to grow. And the roots are creating a pressure on the rock. And it turns out that tree roots are really, really strong. Now, maybe you're a fan of the Marvel movies, and there's a character called Groot. Hey, he's a pretty tough dude. They base it on the idea that tree roots actually do sometimes break rocks. So that's where they put the character of Groot being as tough as he is. So over time, as the root grows, it can actually crack that rock and make the crack bigger and bigger and bigger. And that may lead to breaking the rock. Abrasion. All right. Something that's abrasive is kind of scratchy. So one of the best examples I can think of is sandpaper. Now, if you had some tough sandpaper and you took it to the surface of a rock and just started working on it long enough, you'd probably work some of the grit off your sandpaper, but you may, over time, with enough use, actually wear down some of the surface of the rock. Imagine a sandblaster. Okay? A sandblaster uses a stream of air that picks up some really, really fine sand, and then you blow it onto another surface to abrade that surface. Maybe you're trying to clean old paint off of a car fender or something like that. That's abrasion. Okay, so the air by itself isn't usually real abrasive, but if the moving air is picking up other little particles, other little bits of grit, that can be very abrasive. Water, a stream of water carrying little bits of grit is sometimes used to cut through blocks of stone for making, if you were making granite countertops and things like that, they might be using water jets to actually cut the granite. Now it's not just water, it's water carrying a little bit of abrasive, a little bit of grit with it. So abrasion is when little particles are carried along, and as they bang into the rock, they break off little bits of more pieces. This one I think is a little bit tough for a lot of kids to understand. It's called exfoliation. Maybe you have an exfoliation routine in your skincare routine. I don't know. But we're talking about exfoliation rock. So I want you to imagine a rock that formed down in the earth under high pressure. And over geologic time frames, that rock gets exposed at the surface. So now it's not under the same pressure that it used to be. And, plus now the sun comes out, heats up the rock, and the surface of the rock's trying to expand. And what happens is, because it's not being squeezed under that pressure in the earth anymore, it expands and it breaks up along the surface. Pieces of the surface of the rock break and fall off. That's called exfoliation. The surface flakes away. So now we're going to move to chemical weathering a little bit. And so water. Water can dissolve, excuse me, water can dissolve some minerals. Not all minerals, some minerals. Especially if the water is a little bit acidic. So, acid rain. Okay, if you have rain falling downwind from an industrial area, there's that rain that's falling is going to be a little bit acidic. And so as that rain now seeps through the ground, it can dissolve minerals. This picture is not very good. So the idea here is that it's raining on the ground, and the ground is some of it's dissolving down here, and so it creates kind of a cavity. So that cavity could be a cave. And eventually things can get to the point where the top falls in and you have a sinkhole or something like that. But basically chemical weathering, if water or acidified water dissolves some of the rock itself, some of the minerals out of the rock, that's a form of weathering. Oxygen. Oxygen makes things rust. So here's a picture, and you probably can't see it the best, but you can probably see two different colors. It's two piles of chain. Okay, here's some nice shiny new chain. Here's some old rusty chain. Here's what used to be a boat, a ship, and it's been sitting out away from the water for a long, long time. And it's just a pile of rust, and pieces of it are degrading and breaking apart. So oxygen reacts with substances in a process called oxidation, and in some of those cases the substances that are formed are brittle and fall apart. And so this ship, given enough time, is just going to be a pile of rusty minerals. When oxygen started being produced on our Earth rusted. Okay? When you look at pictures of the Grand Canyon and you see all those reddish colored rocks, the reason they're red is because they're a little bit rusty. there's iron in some of those minerals, and the iron rusted. So we're going to move on from weathering, which is the breaking down of the rock, to erosion. Erosion is the transport. Okay? Erosion has to do with, things being moved around. When farmers are worried about soil erosion, they're not worried about the rock being broken down. They're worried about the soil, the broken down rock that's already out in their field, is going to wash away and end up in Louisiana. Okay, that's erosion, the transport from one place to another. So, erosive forces, moving water. Okay, when rivers flood, the water is not nice and clean. Okay, so I have a picture of a river, and this, the water looks pretty high. I would say this is a flooding situation. And if you look at the color of the water, it's not nice and crystal clear. It's not, reflecting blue sky or anything like that. It's brown. And you got to ask yourself, why is the water brown? And I think it's because the water actually has mud stirred up in it. Well, what is the mud? Mud is little particles of soil. What is soil? Well, soil is effectively broken up rocks and other materials. So as this water is flooding and moving around, it's actually carrying with it soil and rock bits from one place to another. Now, the faster the water is moving, the bigger the particles it can hold. So slow-moving rivers only carry along real fine particles, but faster floods can wash out big rocks sometimes. This again would go with water, but think about waves at the seashore. Water's constantly moving and it's pounding on the seashore, and it can move around the sand. It can wash away. I've heard that there are beaches that, depending on the time of day, on a daily basis, you can go there one time a day and there's this nice sandy beach. And if you come back at a later time, there's no sand, just jagged rock. And it's because the water on a daily basis moves the sand in and moves the sand back out. Now you might think there's probably a lot of abrasion happening in the background too when the sand is being moved back and forth every day. So weathering and erosion work together. The movement creates more weathering. Here's the sandstorm. You have this cloud of sand and dust in the background here. So wind is strong enough to sometimes pick up particles and move them around. Maybe some of you have been involved in ginseng farming or have helped somebody with ginseng farming. I remember as a kid when, even whirlwinds, not anything that's classified as a tornado or anything like that, but sometimes you get those little dust devils that go through, and they can, literally pick up and start throwing around some of the ginseng garden. Maybe you've been out in a baseball game and a dust devil comes through, and boy, you got to stop and protect your face a little bit because the wind can move around those particles. Well, that's an example of erosion. Stuff is moving. Glaciers. There's parts of the world where we have these masses of snow and ice, and they move and they don't stop really for much of anything. And so as they're moving, they're scraping over the landscape. So that scraping is going to have some abrasion action. But then they're going to basically bulldoze forward some of that material. They're going to move material around. Okay? Now that material that's getting moved around, here's a vocabulary term, it's called glacial till. It's been dug up, worked up, scraped up, that's called till. When the glacier recedes at some point in time, it may leave a pile of that material behind. Here's a cool one to think about. It's called creep. Yeah, lovely scientific words. Soil creep. And this is really a function of gravity a little bit. Look at these trees here. And you might ask yourself, well, why did the tree grow this way? I'll tell you, trees grow upward. So why did they do this? Well, when that tree started growing, it was growing upward. But the soil itself, over the years that the tree's been growing, has been shifting down the hill. So the tree's been gradually tilted, but then the tree always tries to stretch upward, and so it ends up getting this curve shape to it. Now, how does that soil creep work? Let's imagine here's a slope, and here's a little particle of soil, and we're going to combine it with that, kind of like the frost wedging or ice wedging. Let's imagine there's a little bit of moisture, and overnight it freezes. So as it freezes, that particle, because of the expanding water, gets lifted off the surface just a little bit. Now this is, zoomed out or zoomed in quite a ways. But that particle gets lifted off the surface. Well, the next morning when the water thaws, the gravity pulls that particle straight down. So it went down the slope just a little bit. Now, this is a huge exaggeration. We're talking about the most minuscule little movement. But then, let's say the next night, the soil freezes and it expands a little bit. Next day, it drops down just a little bit. Repeat that thousands and thousands and thousands of times, and you have a whole hillside that's going downhill. Very slow process, so it's called creep. Sometimes it doesn't happen as a slow process. I'm guessing that this picture isn't showing up terribly great on your screen, but I hope you can see at least some of it. And you see that there's a hillside, and if you can tell, right here is a road. And right here is a large piece of excavating equipment called a backhoe. That's a big piece of machinery, and you can see, its relative size here. And so this hillside gave way and slid down. Now that was not soil creep, that was a rapid happening, and that's called a landslide. Why did it come down? Well, gravity is moving stuff around. Gravity wants to bring things downhill. So gravity is an erosive force. Animals. All right, get a load of this one. This little guy right here, that's a badger. Okay, and he's looking out of his hole. And you can see that in the process of excavating his hole, he's taken a bunch of soil, which is basically just broken up rock, and he's throwing it out, and what tends to happen is, well, it tends to get thrown downhill. Okay? So this little guy has been an erosive force. He's thrown some material around. He's moved it. Okay? Now, someday, he or she is going to move out, and there's going to be this hole left behind, and it may get used and reused many, many times. But you can imagine, too, that some of the stuff that's above that hole over time is going to fall into the hole, so it's falling downhill. So animals, burrowing animals in particular, sometimes move soil around, and they help this process of erosion. Another factor is if you have, let's say, grazing animals, cattle or sheep or something, and they're kept on just one piece of land, and they eat down every bit of vegetation on that land. Now, when it rains or when the wind blows and things like that, those other erosive forces can move more. The water moves more stuff around, the wind moves more stuff around. So that's another way in which animals can contribute to erosion, is if you allow them to overgraze an area. There have been some really interesting studies that show that ranchers out west, if they just keep their cattle moving a little bit, you don't let them sit in one spot too long at a time, so you literally have the old cowboy who, just once in a while spends a day on the horse with their cattle and makes them move so that they don't overgraze any one area. Now you have plants and plant roots that are anchoring the soil better, and you don't get the erosion. All right, I want to check my time here. Well, I was a little bit worried about that. We've already gone 30 minutes, and you probably are getting tired of this. So I'm going to save deposition for tomorrow, and I'll just go with this part for today. Stay safe. See you tomorrow.